Welcome back to yet another lecture. So we've been discussing latches. We discussed the basic SR latch, then the level sensitive latch, and then we discussed recently the D latch. And now from latches, we'll be moving on to what's known as a flip-flop. It's a more practical storage element. And we'll be actually discussing in this video that why we need this transition and what's the difference between a latch and a flip-flop. Fine. So you know that a level sensitive D latch, it had a potential problem that an input can pass to the output at any time during the clock high pulse. And I've drawn here a timing diagram, and this is with regards to this D latch. I've shown only one output DAG because I told you that this is the main output we are interested in. So I have the input D, I have the clock CLK. Clocks are typically represented by this small notch. This shows that this is a clock input anyways. So and Q is my output. So this is my clock signal that is low for some time. It has a low pulse for this duration. Then it has a high pulse for this duration. Like I said, it's a periodic signal. And then this is my D input. It is low for some time, then it goes high, then low and high. So if I am to actually plot the output of a latch, so let's plot here the output of the latch based on the typical behavior of a latch. So up to this instant, let's start from here. The clock is low, so nothing doing. Fine. Now the clock goes high for this entire duration from here to here. And in this duration, whatever happens at the D input, that will be transmitted to the Q output. Now see what happens here initially up to this instant, it goes high. So my output will follow suit. Then again during the same clock pulse it goes low, so it will fall. Of course with some gain delays, I'm neglecting that. Then it goes low. Then at this instant I have the low clock pulse. So it will continue to stay at this level up to this point, and there again is a high clock pulse. It will again track the input. So this is the typical output of a, let me write here, output when it is a latch. Because it is level sensitive, so it will react, it will trigger through this entire duration. What I mean by that is that in the positive clock pulse, this one, at any instant if there is a change in the input data, that change will be transmitted to the output Q. Fine. Now why is this a problem? And to explain this, I have a small circuit here wherein I have cascaded, connected in series, 3 latches. These are latches, so this is a latch, this is another latch, and this is another one. So they are connected in series, which means I have an external input X that goes in the first latch D1. The output of the first latch is connected to the input of the second latch. The output of the second latch is connected to the input of the third latch, and from the third latch you get your external output Y, and they all have a common clock. Now my expected behavior is something that this transition should happen at first clock, then this transition at the second clock, and at the end of the second clock I should actually get my output. No, it actually, because it goes to this, then it will take one more clock from D3 to this. So third clock here. So by the end of the third clock, I should get my input X at the output Y. Right? But does it really happen? Is this the way this circuit will behave? You see, I have the timing diagram here. X is here, it is low, and then it's continuously high throughout. These are my 3 clock cycles. I have clock cycle 1 here, but it will respond only to the positive, so I will only span out the positive levels. Right? Now if I plot them individually, starting with Q1 based on what I am expecting, so Q1 should have behaved like this. It would be 0 up to this instant, then a positive pulse comes, then it should go high and remain high throughout. Then Q2 should have behaved like this. Up to this instant low, as soon as second clock comes, it will have this output and then remain throughout. And finally, Q3 should have behaved like this. Is my expected behavior, then remain high. And this is where after third clock cycle I will get. So this is basically for your reference. I'm plotting here Q1, Q2, Q3, and Q3 is basically your Y. So as you can see, at the onset of the third clock cycle, I should have been getting my output Y. This is the expected behavior. But since these are latches, there is every possibility that in a practical scenario, if I just remove these, this was my Q1. Now there is every possibility that in the first clock itself, because in the first clock Q1 goes high, so there is a possibility that Q2 may also go high because it has the entire this much of span to its disposal. So some way ahead in this clock cycle, something like this, say somewhere here in the first clock itself, Q2 may go high because it reacts to the entire level. So I have this much of time at my disposal. So it may be the case that the clock period is so long that within the first clock itself, Q2 goes high. Fine. Then similarly, Q3 may react in such a way that again within the same clock, yeah, even in the second clock, it will go high because this acts as an input for the Q3. So my expected behavior, wherein I was expecting the output, a valid output at the output Y after three clock cycles, it may not true. I may get the output, the valid output at some earlier time after one clock cycle, after two clock cycles, depending upon the time period of the clock. And the basic problem which actually causes this effect is that your latch, it is sensitive. Like wrote here that it can pass an input to the output at any time during the clock high pulse. So it may happen that your clock high pulse is of sufficient duration that multiple transitions may happen within the same clock cycle. Right? So this kind of creates an ambiguity in your sequential circuits where these latches are used. Like this was a typical example where I had used three latches in series. I was expecting a valid output after three clock cycles, but it turns out if the clock period is sufficiently large, I may get a valid output after two cycles, and in some cases after one clock cycle, which is ambiguous. Right? Now the solution is to design a circuit that I've written here that stores the bit or the D input at the instant that the clock rises from 0 to 1. Now, this is something new. Earlier, we used to have level sensitive. You had the entire high level of a clock at your disposal. Now, what we will be trying is to make our circuits react to only the positive edges. In other words, this is an edge. So earlier it had this entire span for reaction. Now I will try to make it to react only this particular point. Fine. Similarly than this particular point. Now first of all we will see how will it change the behavior of the circuit. For example, consider the same circuit, consider the same timing diagram that I have here. This was the output when it was supposed to be a latch, but what will be the output if it is, and by the way that circuit is known as a flip-flop, huh? If I can achieve something like this. So the output of a flip-flop will be something like it will react. So I have a clock pulse, so it will be 0 up to this instant. Change the color here. Up to this instant, it will be low. Then it will only check the data at this instant. At this instant, my data is high, so it will go high. And then it does not care about what is happening with the rest of the edge. So it will directly go high and then again check the data at this instant. So this will be the typical output of a flip-flop. And you can see the difference. Fine. So these are two things. One is known as level triggering, and level triggering is a characteristics of latches. And then there is edge triggering, and edge triggering is the characteristics of flip-flop. And this is more suitable because it gives you a more predictable behavior. Right? So every time I say latch, it is implied that this will have a level sensitive triggering. What I mean by that is that you will have an entire pulse of a clock, high pulse of a clock at your disposal, which means your circuit can change its state at any point within this clock pulse, within this high clock pulse. And when I say flip flop, it is implied that this will be edge triggered, which means it will only switch data from D to Q. It will only transmit data from the input D to output Q at the instant when the clock goes from 0 to 1. Fine, because this is only one instant, so it makes your circuits more predictable. Fine. So next we'll be discussing how to achieve this edge triggering. How can I make my circuits react, these memory circuits, how can I make them react to only one point rather than and there are many ways of achieving. So we'll be discussing one method, which basically is a master slave configuration that we'll be discussing in the next video.